What's up? In this video, we're going to learn about exponential functions. Very different from the types of functions we've learned about before. So far, we've only learned about algebraic functions. That's when you only add, subtract, multiply, or divide, or raise a variable to a known number. So this includes polynomials or algebraic functions and rational functions or algebraic functions. What we're going to do is what's called a transcendental function, and you don't really need to know that. It's just a fun fact. But this section has two of them, exponential and logarithmics, which are inverses of each other. And then down the road, when we do some trig, tangent functions, that would be an example of a transcendental function. So the definition of an exponential function is when the base of the exponent is known and the variable is in the exponent. So we're only going to have bases that are positive, so don't have to worry about raising like -3 to the x power. Alright, a will always be positive. It'll never equal 1, or else it'd always be constant, right? 1 to any power is 1. And then x will always have a domain of all real numbers. So when we do domain of an exponential, it's always going to be all real numbers. The range will vary, and we'll look at that. So let's see what a graph looks like. So here's a very basic exponential function. Y equals, or f of x equals 2 to the x. So when we plug in -4, we're going to get 1 over 16, because 2 to the -4 power is equal to 1 over 2 to the 4 power. So that's how we get that. And then 1/8 and 1/4, 1/2, 1, 2, 4, and 8. So now if we graph an x and y axis and we plot these points, -4, 1/16, -3, 1/8, -2, 1/4, -1, 1/2, 0, 1 is our y-intercept. Oh, sorry. And then 1, 2, 2, 4, 3, 8. Exponential functions are going to have this general shape to it. Alright, so a couple important characteristics. One is this y-intercept, or this special point. So the special point we're going to talk about is any point where the x value makes the exponent 0, because we know that anything to the 0 power is 1. So it's a very easy point to find. Alright, there's also an asymptote at y equals 0, so the x-axis, and all exponentials will have a horizontal asymptote, and they're going to be shifted up or down. So because it's y equals 2 to the x and it's plus 0, that's why there's an asymptote of y equals 0. If I added a plus 1, then everything would shift up 1. And that's because this term right here can never be 0. It's always going to be positive, but as x approaches negative infinity, you'll see that these values will get closer and closer to 0. Because like when x is equal to like -1,000, y is going to be, that's a y, is going to be 2 to the -1,000, which is 1 over 2 to the +1,000. So it's 1 over a very big number. So even when x approaches these really huge negative numbers, close to negative infinity, you're just dividing 1 by that number, so it's going to get closer and closer to 0. Alright, so that is a basic sketch of an exponential function. So growth is on the right in red. So when the graph is increasing, it's called exponential growth. The domain's all real numbers. The range is y is greater than 0 because of the asymptote. The y-intercept, as we saw, was 0, 1. It's increasing, and it's continuous. Exponential decay is when the base is less than 1 but greater than 0. So 1/2 would be like the reflection of y equals 2 to the x over the y-axis, because if we took that and replaced x with -x, so that's a reflection over the y-axis, that would simplify to 1 over 2 to the x, which is the same thing as 1/2 to the x power, because 1 to the x power is just 1. So that's why when you negate the exponent which is a variable, it'll reflect it over the y-axis, because that's the rule for reflecting over the y-axis, mapping x comma y to negative x comma y. And you could also do that by finding the reciprocal of the base. So if you just change 2 to 1/2, it's the same thing as putting a negative in front of your x. So both of these, the red and the blue graphs, f of x and g of x, will have domains that are all real numbers and ranges that are y is greater than 0, because we just reflected over the y-axis. The y-intercept is 0, 1. It's decreasing. And the asymptote's at y equals 0. It's continuous, so a lot of things in common, but the main thing is one is growth and one is decay. So when graphing exponential in this form, we're going to first look at b. b is the base of the exponent. If it's greater than 1, it's going to be growth. If it's in between 0 and 1, it's decay. So that's going to affect the shape of our graph. And then we're going to find a special point. So a special point is just the x-coordinate for like what makes the exponent 0. So if you set cx minus h equal to 0, you get h over c for the x-coordinate, and then plug that in, and you find the y-coordinate. And it's very easy to find because it's going to make this whole part right here equal to 1. So it's just going to be, a plus k. That's what f of h plus c is. The asymptote is always going to be correlated with the shift up or down, so the vertical shift. So that number will tell us our asymptote. And if a is negative, so that could be a reflection. So if you negate the entire function, put a negative in front of f of x, that's going to reflect it over the y-axis. So it's just going to reflect over the asymptote if you reflect after your translations. But if you do it at the beginning, it'll just be reflecting over the x-axis. So let's graph these. So first thing I'm going to do is, doesn't really matter, but let's find the asymptote. So I know it's going to be up 1 from that plus 1. So there's, oops, this is really ugly. I want to start all over. Demand perfection from my graphs. Alright, so here we have an asymptote, a vertical asymptote at y equals 1. Alright, then I'm going to find a special point. So it's going to be at f of 2, because that is what makes my exponent 0. So that's going to be 1 plus 1 is 2. So I know the point 2, 2 is on my graph. And I know it's going to be exponential growth because of the 3, and there's no reflections. So my graph is going to look like this. It's going to have an asymptote at 1. Bada bing, bada boom. Alright, I know the domain is going to be all real numbers because all exponentials have those domains. I know the range is going to be y is greater than 1. And if I need to find another point on my graph, maybe plug in 3. So try like f of 3, because I know it's going to give me 3 to the first power plus 1, which is pretty easy to find. And you get 3, 4. So 3, 4 is right there. So there's my other point. So there we go. Bada bing, bada boom. Got 2 points and a nice graph. Alright, let's try that again. Alright, now we have a decay model. I know it's decay because of this base of 1/2. So let's sketch a graph first. So I know, let's see, my asymptote will be at positive 4. So 1, 2, 3, 4. That's because of the plus 4 at the end there. So y equals 4 is my asymptote. Alright, let me find a special point. So a special point would occur at x-coordinate -3, because that's going to give me, alright, at some point this got paused. I don't feel like looking back and finding out, but I don't know what you missed. But a quick recap, there's an asymptote at y equals 4 because of the plus 4 at the end here. And now I'm finding a special point by plugging in -3, because that's going to make my exponent 0. So I have 3 times 1/2 to the 0 power, which is just 1, and then plus 4. You could tell, yep, that's a plus 4. So I have a 7 there. So I know there's going to be a special point at -3, 7. So 1, 2, 3, that's 4, 5, 6, 7. So right here, -3, 7, and it's going to be a decay model. So it's going to look like this because of the 1/2. And there we go. Bada bing, bada boom. that's what the graph looks like. If I need one more point, then I don't know, plug in one that's easy to find. So I know 1/2 to the -1 power is going to be 1. So if I just plug in -4, I get 3 times 1/2 to the -1 power plus 4. So that's 3 times the reciprocal of 1/2, which is 2, plus 4. So I have 6 plus 4 is 10. So I also have the point over here, -4, 10. And there you go. So there we have an exponential graph with 2 points. Got an asymptote. We got a domain of all real numbers and a range of y is greater than 4. All right. Compound interest formulas come up in this section, come up on standardized tests. Important to know if you're going to have a bank account, like 21 Savage one day. So if you don't have one already. So there's just formulas that we're going to plug in and plug and chug and evaluate. So T in the formula is years. So if they tell you 13 months, that's going to be like 1 1/12 of a year. Balance A, so that's what's in the account given the principal. Principal is what you invest, like what the original value is. So if it's not an investment, if you bought like a car, what the initial value of the car is, P, and whatever the starting value is going to be P. The rate is always going to be as a decimal. So if it says 2%, you're going to plug in 0.02. It could be negative. It could be a depreciating asset that loses money like a car. So if the rate's negative, then you plug in negative, the decimal version of the rate. And if it says compounded, n times a year, so compounded yearly, n is 1. Compounded quarterly, that's 4 times a year, n is 4. Compounded monthly, that's 12 times a year, n is 12. If it says compounded continuously, you're going to use a different formula. Notice how there's no n in the bottom formula. So if they don't tell you how many times you're compounding specifically, if it says compounded continuously, you're going to use the PERT formula. So let's say you invest $20,000 into an account that has an interest rate of 3% a year. Find the amount in the account after 5 years if it's compounded monthly. So the amount in the account is A equals P, so P is the principal. That's 20,000 times 1 plus the rate. The rate is 3% a year, so it's 0.03 over N is the number of times compounded a year. So if it's monthly, N is going to be 12. And then to the NT power. So if it's compounded monthly for 5 years, you're really compounding it 60 times because it's 12 times a year for 5 years. So that's why the exponent is going to be 60, which is the same thing as 12 times 5. So when you're compounding monthly, instead of getting 3% a year, you're getting a 12th of 3% 12 times a year. So you actually make a little more money that way. Type that all in a calculator. You type that into a calculator, you get $23,000, $232.32. That's a lot. Actually 34 if you round up, because it's 33.5. So I was going to say a lot of 3s and 2s, but that 4 had to ruin the party. Now if you compound continuously, you're going to use the PERT formula. So P times E, which is a constant. Alright, E is a number that you could find on your calculator. I'll show you in class. It's about 2.7 to the RT power. So 0.03 times 5. Type that into a calculator, and you get $23,236.68. So the more times you compound it, the more money you'll get, but not by a lot. So you made $4 more if you compounded continuously rather than monthly. So compound interest problem is just about plugging in to a formula correctly. And well, that's the last slide, folks. You're off the hook. Don't have to watch anymore. Hope you liked it, and I'll see you in class.